Hello everyone, my name is Tisha Amadea Susilo, student ID 0361712, and within this video, my groupmates and I from Group 12 of Section 5 will be discussing the implementation, insights, and findings of data mining techniques we explored within this group assignment. To preface, within this assignment, our group explored three problem statements, each aimed to be solved with separate data mining techniques. The first one being ambiguity in determining victims as either inpatients or outpatients. This problem statement causes uncertainty in delivering the appropriate medical attention and care to mitigate overdose symptoms of the appropriate victims. Classification techniques will be explored to solve this problem statement. The second one being difficulty in distinguishing between drug users and drug abusers. This issue may complicate the establishment of legal limits of recreational drugs and targeted rehabilitation programs to the suitable demographics. Clustering techniques will be explored to solve this problem statement. The last problem statement we'll be going over is the difficulty in identifying fatalities caused by a singular drug type. Overlooking these anomalous cases may lead to lost insights regarding potentially lethal drugs that cause fatalities even when consumed independently. Anomaly detection techniques will be explored to solve this problem statement. Prior to applying any of these data mining techniques, pre-processing was done beforehand to handle any inconsistencies within the dataset. These include handling missing values, standardizing values, value encoding, as well as feature engineering to create a new and improved clean dataset that we can work with.
Hi, my name is Wang Shuer. My student ID is 0368302, and I will be explaining about the classification techniques we did to distinguish between inpatients and outpatients. Three classification techniques were done within this report. These include decision tree, random forest, and k-nearest neighbors. Before applying any classification techniques to the dataset, some pre-processing methods were done to ensure better and more accurate classification. First, all necessary libraries are imported and the dataset is loaded. Then, any missing values that may have been left over are removed. The assign patient type function performs feature engineering, which classifies patients based on hospital location data through the binary patient type categories, inpatient and outpatient. Next, any irrelevant columns were dropped. Patient type is encoded to 0 for inpatient and 1 for outpatient. Categorical features are one-hot encoded and numerical features are standardized using standard scalar. Finally, class imbalance was handled using smoke tomac, which not only balanced the dataset but also improved classification accuracy by eliminating ambiguous samples and defining clearer decision boundaries. The first model is random forest, which trains many decision trees and combines their result for better accuracy. Let's look at the implementation. We imported random forest classifier and used randomized search CV for hyperparameter tuning. By testing 10 different hyperparameter combinations using 10-fold cross-validation, we optimized the model for weighted F1 score. After selecting the best performing model, we trained it on the dataset and made predictions on the test set. And results showed that during cross-validation, random forest achieved an accuracy of 71.74%. However, on the test set, accuracy dropped to 62.89%, indicating potential overfitting. The classification report also revealed that outpatients were classified more accurately than inpatients. The confusion matrix confirmed this fact by showing case that 16 inpatients were correctly classified, but 22 misclassified were not. This result shows that random forest struggled to distinguish inpatient from outpatient, possibly due to class imbalance. Overall, we discovered that the random forest was not the most suitable. Next, we test the decision tree algorithm, which classifies data by splitting it based on feature values, making sequential decisions until reaching a final prediction. While decision trees can sometimes overfit, we addressed it by limiting the maximum tree depth to balance complexity and performance. For implementation, we imported decision tree classifier and initialized it with key hyperparameters, setting max depth equals to 50, min sample split equals to 2, and min sample sleeve equals to 1 to control node splitting and prevent unnecessary complexity. After training the model, we evaluated its performance on the test set. Decision tree achieves the highest test accuracy among all three models with 65.98%, closely matching its cross-validation accuracy of 65.87%. The classification report showed higher recall for outpatients, which was 76%, but weaker performance for inpatients at 50%. The confusion matrix confirmed this, showing that 45 outpatients were correctly classified, but 19 inpatients were not. Despite this, decision tree demonstrated strong overall performance and the best balance between training and test accuracy among the model tests. The final model we tested was K-nearest neighbors, which classifies data by finding the K-most similar points using distance metrics like Euclidean distance. For implementation, we imported K-neighbors classifier, applied robust scalar for normalization, and used PCA to reduce the dataset to 5 key components. To optimize the model, we used grid search CV to find the best K value with 5-fold cross-validation and train the model using Minkowski distance, P equals to 2. The cross-validation accuracy was 62.83%, but test accuracy dropped to 57.73%. The classification report showed that outpatients were identified correctly 83% of the time, but only 18% of inpatients were classified correctly. The confusion matrix shows that KN has strong bias toward outpatients, with 31 inpatients misclassified, making it weakest performer overall. Among three models, decision tree performed the best, achieving the highest accuracy, along with balanced precision, recall, and F1 score, making it the most reliable for classifying inpatients and outpatients. It offered the highest accuracy and balanced performance, making it the most suitable for the classification task within the report. That's all for me. Thank you.
Hello, sir. My name is Tang Yu Xin, student ID 0363679. Today, I will present an evaluation of different clustering techniques implemented within this report. We implemented 3 clustering methods, which are K-means, K-moods, and dbScan on 3 different sets of geography location data and assessed their performance using key evaluation metrics such as silhouette score, Davis-Bodley index, and Kalinski-Harabas. The first clustering algorithm used was K-means, which is a method that groups numerical data into compact clusters. The second algorithm was K-moods, thought designed for categorical data, was tested here for comparison. Finally, we used dbScan, which on the other hand formed cluster based on density, making it useful for irregular shapes. For injury location, K-means performed best with the silhouette score of 0.467 and a DBI score of 0.854 and a chi-score of 9952.836, indicating well-separated clusters. For K-moods achieved a silhouette score of negative of 0.162 and a DBI score of 1.598 and a chi-score of 135.762. Showing weak cluster ability. For dbScan had a higher silhouette score of 0.765 but a high DBI score of 2.339 suggested overlapping cluster, while the chi-score of 2433.803 indicating moderate separation. Overall, K-means was the best performer due to its better balance of compactness and well-defined structure. For residence location, K-means again shows strong performance with a silhouette score of 0.454 and a DBI score of 0.866 and a chi-score of 9700.856, maintaining a good balance of compactness and separation. For K-moods perform poorly with a silhouette score of negative of 0.167 and a DBI score of 1.581 and a chi-score of 125.677, confirming weak cluster. dbScan achieved the highest silhouette score of 0.763 and a DBI score of 1.971 and a chi-score of 1874.341. So overall, K-means proved to be the better choice as it maintained the balance between compactness and separation. For depth location, K-means emerged as the best performer with a silhouette score of 0.43493 and a DBI score of 0.8 837 and a chi-score of 8723.588, forming strong and compact cluster. For care modes performed the worst with a Salivate score of negative of 0.228 and a DBI score of 3.761 and a chi-score of 48.91, indicating weak clustering. For DB scan had the highest Salivate score of 0.873 and DBI score of 2.071 and a chi-score of 1485.614 suggested some cluster overlap. So overall, Camins is the best performer among them. In summary, while DB scan consistently achieved the highest survey score, suggesting clear cluster, it also showed a higher DBI index, indicating overlapping clusters. On the other hand, Camin consistently had the lowest DBI and the highest chi index, proving that it performed denser and more compact clusters. Across all datasets, Camis emerged as a best clustering technique, demonstrating the most balanced performance in terms of cluster separation and compactness. That's all for my presentation.
For anomaly detection, three techniques were explored, which includes isolation forest, one-class SVM, as well as local outlier factor. Now let's look at the code for each of these implementations. Generally, all three implementations follow the same steps: initialization, fitting of data frame before it makes predictions, and then it is evaluated. Let's start with isolation forest. The isolation forest model is initialized with the following parameters of n estimator 400, max sample 0.5, contaminator 0.5, max feature 1.0, bootstrap true, as well as random state set to 42, which ensures reproducibility. The model is then fitted using the previous created data frame to make its predictions. Additionally, the percentage of anomalies was also calculated to see how much of the dataset was flagged as anomalies, and lastly, the results are printed. The results showed that a total of 49.71% of the data was flagged as anomalous, which is logically impossible. However, it did manage to detect the appropriate anomalies where only one certain drug is present, as seen within the drug count feature on the screen. Okay. As seen by the confusion metrics as well as the classification report, the quote-unquote perfect classification depicted that the confusion metrics flagged a total of 4,510 data points as normal, whereas the rest 4,458 data points were flagged as anomalous. This is highly unlikely in real-world applications of anomaly detection tests. This also indicates that this model may be overfitting the dataset. The model also achieved a 0.32 ROC AUC score, which indicated overall poor performance. Now let's move on to one class SVM. Once again, the model is initialized, fitted, and then it can make predictions and is then evaluated. As seen by the output, one class SVM actually successfully detected all the cases where only one drug is present, and a total of 85 records were flagged as anonymous and 8,883 records were flagged as normal. The confusion metrics also showed a more realistic performance compared to isolation forest, with some normal records being misclassified as anomalous instead. The overall performance made more sense compared to isolation forest and would be more viable in real-world applications. 83 actual anomalous data points were successfully identified. However, 24 normal data points were flagged as anonymous instead. A total of 8,859 actual normal data points were also correctly identified, and 0 anomalies were classified as normal. This model also scored a 0.99, which is an almost perfect score, which indicates a near perfect distinction between normal data points and anomalous data points for this specific model. And lastly, I'll be going over local outlier factor. And lastly, for local outlier factor, the model is once again initialized, fitted into the data frame, and makes predictions, and lastly is evaluated. For local outlier, the parameters were set as A neighbors 800 and contamination of 0.02, and this model managed to detect a total of 151 anomalous rows. As seen by the confusion metrics and the results of this model, the local outlier factor had a moderately higher performance compared to isolation forest, however, did not perform as well as one class SVM did. 151 true anomalies were correctly identified as seen by the confusion matrix, whereas, however, these anomalies also included records with two or more drugs present, which slightly deviates from the original problem statement that we were aiming for. 1,715 predicted anomalies were classified as normal, which resulted in a higher rate of false negatives, followed by 7,074 actual normal data points were correctly classified as normal, and lastly, 28 normal data points were actually misclassified as anomalous instead. The local outlier factor model had an ROC-AUC score of around 0.58, which indicates moderate to high performance. Overall, in terms of this report's anomaly detection objectives, one-class SVM ended up being the most viable and best performing anomaly detection technique with high accuracy, precision, recall, and F1 scores, as well as a 90.99 ROC-AUC score. Though these values showcase strong anomaly detection, there is still a possibility of overfitting within the dataset. Even though, as seen by the table, isolation forest has an overall higher performance and a higher ROC-AUC score, these results that we obtain from implementing isolation forests greatly deviates from real-world applications by flagging half of the dataset as anomalous, which is logically impossible. Now I'll be going over the data visualizations of the results that we obtain from each objective. These are the data visualization pie charts of the results that we obtained from implementing classification techniques to identifying victims into either inpatients or outpatients. For random forest, we got a ratio of 30.9 inpatients compared to 69.1% outpatients. For decision tree, we got 34% inpatients and 66% outpatients. And lastly, for K-nearest neighbors, we got 17.5 inpatients and 82.5 outpatients. By identifying these common occurrence of drug-related injury patterns, with most of the victims being outpatients, medical professionals and emergency response teams should reconsider equal criteria for both inpatients and outpatient admissions within potential overdose cases, trying to mitigate and lower the mortality rate of outpatients and make sure that both kinds of patient types receive the same amount of medical care in order to mitigate their overdose and try to prevent a potential fatality or a death. These are the data visualizations obtained from the clustering algorithms, which all roughly had the same distribution with a geolocation for death showing a higher percentage of drug users with 63.8% compared to 36.2% drug abusers. Drug abusers, as we can see by the pie charts, make up a large portion of the entire records, indicating that there has been a low success rate of existing drug rehabilitation or drug abuser management techniques. With these insights that we have discovered through this experiment, government officials can fine-tune their rehabilitation programs and make sure that they are targeted at the right target demographic, as seen by the scatter plot, which is visualized in the report. Lastly, these are the data visualizations from the anomaly detection techniques. For isolation forests, we got 50.3% normal and 49.7% anomalous. For one-class SVM, we got 1.2% anomalous and 98.8% normal. And lastly, for local outlier factor, we got 1.5% anomalous and 98.5% normal. As seen by the flagged anomalies, disregarding isolation forests, of course, a large majority of these cases had the presence of opioids, indicating that opioid is one of the most dangerous and fatal drugs which tend to cause thousands of deaths even when consumed independently from other substances. These records, which only had opioid present, were the records which anomaly detection algorithms flagged as anomalous within this dataset. In conclusion, this report examines how classification, clustering, and anomaly detection techniques perform in various applications, specifically within this instance on a medical dataset. Each of these algorithms have their own pros and cons, strengths and weaknesses, and no technique is absolutely perfect because their effectiveness and performance depends on both the data structure and the target problem statement for analysis that we are doing. Due to this video's limitations, please refer to our report for further details on more insights that we uncovered within this report. That's it for our video. Thank you so much for watching.